Okay, V is a vector, lambda is a scalar. We say V lambda is if matrix. Yeah. Okay. So V is a vector. We say this night. Who cares? All right. One of the things that you need to learn in solving problems is the terminology here doesn't matter. That's in their human interest story. Good for us. We know some German word now. But the important thing is this equation. That's it. N by N matrix of V is the same thing as that number. So let's see what the question actually asks. Suppose that P is an N by N invertible matrix. So suppose you have an N by N invertible matrix, we will call it P. It says show that lambda V is a pair for A if and only if lambda P inverse V is a pair for P inverse A. Show lambda V is what's perfect is the numbers of seconds vector is an eigenvalue eigenvector pair. Is an eigenvalue eigenvector pair. And it says hint. B is BP inverse B. Okay. Suggestions. Let me break this down. How about that? Let's simplify the question. We've got two conditions. We need to show the same thing, right? Lambda V is an eigenvalue, eigenvector pair for X words, or what does that mean? What does it mean for lambda V to be an eigenvalue, eigenvector pair? It means that right? Because that's what it says on the test. And it says, show that this is the same thing as this being an eigenvalue, eigenvector pair for this. Right? Well, let's write down what that means. The role of A is now being played by old Pat here. Everybody agree with that? And what's my vector here? Gotta show these two things the same. Everybody agree with it? Everybody okay? That's sort of what we imagine this. We need to show the P inverse of V is the vector and the same lambda with this matrix here. Okay with that? Any ideas what to do now? What's that? Okay, right, so is this what you mean right here?
I was meaning on the other side.
Oh, cancel these two?
Yeah.
You can't do that,
Can't do that.
right, because you can't switch things around necessarily, usually. You can't. Yes,
You could factor out a P inverse on both sides.
okay, yeah, that's right, you could factor out a P inverse on both sides. Everybody see that? So, for example, take this equation. So this is a reimagining of what you said. Let's multiply both sides of this equation by, so suppose we have this equation, we multiply by P. Everybody okay with that? It's like alphabet soup, right? But actually, it's not so bad. What happens to the P inverse here? It's Casper, it's gone. And what happens to P inverse here? It's gone as well. So what is left over here when the bloodshed is through? What's the only thing left standing? Agreed? What about the other side? Is there anything you cancel here? Generally, you can't swap matrices. That's just a number, right? So I can pull the number out front. But what happens to PP inverse? It's just the identity, right? So what's left on this side? Everybody okay with that? So I started with this, and I got this. All right, okay? And that's what I was asking. You technically have to start here and go back here, but how could you start here and get back here? Yeah, because this says if and only if. So if you have this being a pair for A, and the other one has to be a pair for this, and if you start here, so what we did is if this big one was vector and lambda was scalar here, then it means that this equation holds. We need to show if this equation holds and this equation holds. But how do we do it? Don't worry too much. Just do everything that you did in reverse. Put everything back, right? So how can you go from here to here? Put in a PP inverse, right? And put these PP inverses on both sides here, right? Everybody agree with that? So we can start here. We can put PP inverse here. And I can put PP inverse here. That's the same thing as AV, right? Everybody agree? And then I can put this back the way it was. And now just multiply by P inverse and you get your original equation. Yes,
How do you know that A goes with the first B? First-
you mean right here?
Yeah.
Because I said so. I mean, it was just in the problem. Right, that's something that you're getting from. Yes,
I think it's formally that like. Making P versus EP.
what's that now?
How would you like start off with that?
Because it says in the problem. Oh, okay, so. This is what does it mean for an eigenvalue, eigenvector pair? It means AB is length. Right? Matrix times V is lambda times. Right? You okay with that? So what is it, an eigenvector pair for this matrix? Matrix times B. So that's PA inverse, well, actually, right. Matrix times vector is lambda times vector. So matrix times this thing, here we go, is lambda times. Same vector with the lambda, same vector. Right, different? When you start off, I think that was actually one of the tough ones on that particular. Okay, others. Yes,
Do one C and one C, one D on
let's see one D on
was nine.
quiz 9.
I think it's just the dimension of it.
Oh, once with, yeah, I'm glad you said that, because I actually didn't know. Okay, so there were, a lot of you did like mostly okay on this, but on the exam, I don't want you to miss any of it. That would be great. So suppose A is, no, it was 8.5, I believe.
Yeah.
By the way, since I know it's coming up, what do you know about the size of the transpose of this? It is reversed, right? The row becomes columns. Okay, so far, the questions, as I remember them, are, down here. Then repeat it for the transpose. Okay. Okay. So for the first one, number 1. So notice for 1 and 2. We have what? An 8-row by 5-column matrix. So it's got 5 columns, all of which are 8 high. So what's the minimum for the column space? Right, okay, for example, this matrix would be all full of zeros, right? I mean, it could be. For example, the 0 matrix. Since the dimension can never be negative, I mean, that's as low as you can go, right? how about the max? Right, you could have all 5 of those columns could be pivot columns, making them all linearly independent, right? And so the column space, if they're all pivot columns, then that's the dimension of the column space. So it can be as big as. Okay, now we have the null space. Remember, the null space is you're looking at the set of all solutions of the homogeneous equation, right? So the null space here, what does the null space live in? The column space lives in, okay, yeah, so where does the column space live? Its maximum dimension is 5, but where does it live? It's a subspace of what? No, I'm asking what dimension or what? The column space is a subspace of R what? No, there are 5 columns, but how big are the columns? 8. They're all 8 tall, right? So the column space is a bunch of 8 tall vectors, right? So it lives in R8. So that first one actually lives inside R8. The null space actually lives in R5, right? Because it's stuff that's killed by this. So what's the minimum dimension of the null space? How would you figure out the null space? Well, think about what you would do if you actually had to compute something here. Of course, just like almost everything else, you can basically reduce it down to row reduction, all right? So suppose you've got 8 by 5 matrix and you row reduce those 5 columns. When you look at your file row reduced thing, how do you tell what the dimension of the null space is? The number of free variables. What's the minimum number of free variables you can have? You could have 0. But equivalently, all these columns might be linearly independent. We've got 5 vectors inside of R8. It's the biggest null space. It could be all of R5, right? In fact, if that sucker is the 0 matrix, the null space is everything. It's all of R5. Like, cool with that? Well, now when you take the transpose, you now have 1, 2, 3, 4, 5, 6, 7, 8 columns, and they're all 5 high. The column space now lives inside of what? R5, because all the columns are 5 tall. Everybody agree with that? So column space lives in R5. Okay, so what is the minimum for the dimension of the column space? Also 0, right? Because again, all those columns could be 0 for sure. What's the maximum? Right, so that's right. If you look at the column space, how do you tell what the dimension is? It's what, the number of pivot columns, right? Everybody agree with that? How many pivot columns can we have? We can only have 5. I know you're tempted to say more, perhaps, but you're limited by the number of rows, right? Everybody agree with that? So this is actually max 5. Like, finally, what about the null space? The null space for this one lives in R what? R8, because this is a 5 by 8 matrix, null space in R8. What is the yeah.
3, because you can only have 5 pivot columns.
Okay, so you can have at most 5 pivot columns. I mean, you gotta have at least 3 that are not pivot, 3 free variables. That's exactly right. The null space with this guy has to be at least 3-dimensional, at least. What about the max?
8.
Again, these should all be 0 columns and everything, so it can be 8. By the way, how many columns does this matrix have? What's 0 plus 5? I feel like maybe you'd ask, what's 0 plus 5? How many columns does this matrix have? 8. 0 plus 8? What theorem did I just use to check myself? Right, that's rank-nullity.
What's called?
Oh, it's the rank-nullity. Yeah. Okay. Another question. Yes, that's the one where we, can you give me the vector?
Yeah.
Here, let me get this vector. Okay, so we'll tackle this next one. Okay, so what our P one is
101,
101.
021.
And the first question is what? Okay. So when I say explain why it's basis, you gotta tell me why. Some of you said, oh, a basis is linearly independent and it spans. Yes, that's absolutely true, but that doesn't explain why this is basis, right? So we gotta figure it out. What's the best way that we can go about figuring this out? Yeah, I mean, do that. Let's row reduces. It's a basis if and only if it reduces to what? Identity. Or actually, all you really need, we don't have to go all that way if we don't want to. Because all we really need is we need there to be a pivot in every row and we need every column to be a pivot column. And I think that would be readily apparent pretty quickly. If I take this animal, let's see, 1, 0, 1, 0, 2, 1. If I multiply by -1 and add that, I get 0, 1, 0. Do I agree with that? Multiply this by -2 and kill this. Turn that into a big zot. Everybody okay with that? And then flip this out. It's clear, isn't it, that there's a pivot in every column and not a pivot in every row, so it's basis. That's probably the quickest way. Some of you did that by, I saw a couple of people set up the equations and show that they're linearly independent and to make some kind of argument they span. That's great. This will probably be quicker for you though. Okay, so now you know it's basis. I also asked you to express 4, 5, 6 in terms of this. Okay, you guys want to see that? Well, people did this different ways. Some people did it by like, you know. This one you can actually do. Some people did this by, you know, using the force or something. So if you wanted like, you need to find columns A, B, C. I think the vector was 4, 5, 6, wasn't it? You know, if you put your eyeballs on this, this means that A plus C is 4. This means A plus B plus C is 6. So you subtract those two equations, immediately get what B is, and then you can kind of back substitute. And that's great. You can do that here. But let me give you something here's something that's a little bit more practical. And this worked out well because the numbers work out well and so forth, but it might have been less clear, it was more complicated. What I would do really is to solve this is just solve the augmented equation. One, and then put it back. This systematic way that we do things, I think there's, in the long run, it's quite quick. So this becomes 1, 0, 1, or subtract it of this. Subtract 0, 1, 0, 2. And at this point, I might bail. In this particular case, because it's so easy now, at the following sense, x2 is 2. That equation is immediate. And then I get x2 plus x3 is 5. But I know that x2 is 2, so this is x3 is 1. And now the first equation will get away because I have x1 plus x3 is equal to 4, and this is 1, so x1 is 3. So we get 3, 2, 1. And again, I totally get it that you might not have time on a test or a quiz or whatever, but this is checkable, right? If you put x1, if you multiply this one by 3, that's your x1, this one by 2, and this one by 1, and add them up, you should get 4, 5, 6, right? Any questions on that? Okay, others? Yes.
So for all 2022, is time.
Let me catch up to you here. Fall 2022. There's 9. Okay. Is this, for this problem, we produce a different coordinate system for R squared? Show that, okay, so I give you these two things. First question. Show 1, 1, 1, 2. Is the basis. Okay. Let's just go to some matrix. Sure. Let's dispose of this problem as quickly as we can. There's the matrix. All we need is for it to be a basis, is we just need every column to be a pivot column. Everybody agree with that? That's all we need for that square matrix. And so there you go. Every column is a pivot column. So literally right on my paper at this point, every column is a pivot column. So those two are a basis for our squares. Done. Good enough? Now, let's move on with our lives. The next one says, express the vector AB in terms of the basis B. Or I might say B for them. So how are we going to do that? With the equation. So what we have is we need to find X and Y such that X plus 1 plus Y 2 is equal to and for A and B to be. So given A and B, I need to find the appropriate X and Y in this work. Agree? So what do we do? This is just a system of two equations, is it not? That's right. Let's just throw this in a matrix, right? I mean, if I had a nickel for every time I threw some crap into a matrix, right? So let's do it again. You definitely should not let that A be intended. It's gonna work out really well. We're trying to solve for X and Y. Let's make a go of this, right? Let's do just what we did over there. We showed it. Multiply -1 times this and that this. And this should be what? Minus A. We could back substitute at this point, but I'll take your step. So it's fairly easy to do. Now we'll take -1 times this and add this, so I'm gonna have the same bottom of it. And my new top row is gonna be 1, 0. -1 times this, that's gonna be 2A minus. Negative of this, added to this, 2. So X should be so. Is everybody okay with that? Since we have the luxury of time, this is a review session, check it. So if you look at 2A minus B times a factor of 1, 1 plus minus A plus B times a factor of 1, 2. Let's see what happens. It becomes 2A minus B, 2A minus B plus minus A plus B minus 2A plus 2. And what do we get? When I add these up, I get 2A minus A is A, minus B and D is 0. Okay. I get 2A minus 2A is 0, minus B plus 2B is B. So it works. So another way of writing this is AB in standard coordinates is equal to 2A minus B minus A plus B in B coordinates, where B is set vector 1, 1. Yeah, when we move forward a little bit in this class, we're going to be doing a lot of kind of change of bases, kind of stuff like this. Okay. Other questions? Yes. Second question, quiz 8. And do you mean quiz 8 this year?
Yeah.
And so, like a Dorcas Malorcas, I haven't gotten posted yet. I'm gonna put that question in.
Suppose that, like, we are at, which one to say, is the basis of S, and X is a vector. Explain why X is written, linear combination of vectors. And then part B is explain why X is
Okay, so let me catch it. So if S essentially is Rn, did I get that right?
Yeah,
And what do we have, V1 up to?
B1, two.
Up to Vn, right? Oh, wait a minute, K. Oh, yeah, because it's such a thing. Basis for S.
And then the
Okay, and X. Let's see, one, V1.
Yes. The first part was explained, by X to be written as linear combination of vectors.
Oh, well, and what do we know about X? Just X is in F?
Yeah.
Yeah, X is in S. So, and you want to know why the linear combination factor. Don't read too much into this one. This is just kind of a definition problem. X is in S, and S is the span of V1, V2, right? Because what does the basis do? It's linear independent and it spans. So S is the span of these vectors. Numbers. One, K, with the important thing here is a basis. So here's the big takeaway. A basis spans. A basis of S, say, spans S. And it's linear independent. So we've got that. So is everybody happy with the X being a linear combination of those B's? Okay, and what's the part two question?
Explain why if X one plus two B two or say B1 are finished by
Is uniquely determined? Okay. Right, that's the meat of this question. Takeaway from the question, what you should get from this is when you can write an element in terms of a base, or actually any linearly independent set, that's the only way to write it. Right? And I'll give you an example that kind of illustrates the importance of that. Suppose we could write this some other way. Suppose there are different numbers, perhaps. Suppose I could write X these two different ways, maybe with different numbers. Yes,
So would that contradict it being linearly independent? Then we
yes,
say
it will. Do you know how?
because there's two sets of coefficients.
Right, but how does that contradict the linear independence?
X would be considered a linear combination.
Okay, I think you're on the right track. You have an idea on this?
It would have to be a free variable. It's linear independent, it's not a free variable.
Okay, right. let me, then we'll go with this. I think there's danger getting used on this. Let me ask you this, what is the definition of linear? Let's go back to our rules. Also, that you getting punchline. Yeah. U1, A1, U1, plus A2, U2. If you did ever add up to the zero vector, then what does this mean?
Is it all the A value like uniquely determined?
All the A values in this case have to be zero. That's the definition of linear. Whenever you see, what it means to be linearly independent is whenever you see this equation here, if these things are linearly independent, all the A's have to be zero. Certainly, would you agree that if all the A's are zero, then you get the zero back. But that's the only way to do it. Yes. Okay.
So wouldn't that be one of those?
Wouldn't that be one? Starts to.
One of them is redundant, but is that what that means? It equals zero. That's one of the two effects.
Yeah, well, so yes, it also, you're right, it also means that one of these in the set can be written as a linear combination of the others, right? Thank you for saying that. I'll give an example and we'll illustrate where that comes up to. Do you all remember this? This forces A1 and A2 and all the A's be zero. That's what it means to be linearly independent. So for example, let me give you this vector here. 1, 1, and 1, 0. This is linearly independent. Let me go old school and do this is old fashioned thing. And I think this is kind of an easy one to do. Suppose I have this. Look at the second coordinate. What condition does that force on A?
Number on the left side is zero on the other.
Right, A has to be zero. Everybody agree? Because you have to get a zero on the second coordinate. That's automatic. So that has to be zero. That means A is zero. But if A is zero, that means that now you have this equation here, but now B has to be zero. So these two are linearly independent. You can also put this in a matrix, and if you only get the trivial solution to the homogeneous equation, if the columns are all pivot columns, right? These are all counted together. Everybody good with that? Now, in regard to his comment, let me throw in one more. But the third vector. Any two numbers. What's that? Two sounds good. So notice that if I have 3 times 1, 1, 3. Three, 9. Look at this. There's a linear combination of these 3 vectors. That is the 0 vector. And all the coefficients are not 0. So that's another way to look at it. And the comment that you made, pick one of them. In this case, any of them. All you have to do is pick one without a 0 coefficient. And notice that you can bring this over to the other side, and 3 comes 1, 1, minus 1 times 2, 3 is the vector 1, 0. That is to say, the redundancy, I think you talked about, one of them can be written as a linear combination. Right? These are linearly dependent. By the way, I didn't force anything upon you at all. I just said, give me a third vector. And I almost said, don't make it 0, 0, it's up more. How did I know that a third vector would automatically make that set linearly dependent? Yeah. If you threw those 3 into a matrix, it'd be a 2 by 3 matrix, right? So you got 3 columns, 2 rows, right? No way do you have 3 pivot columns, right? So it has, I knew that no matter what you said, it was going to work out. Let's get back to this. This is the question that we cover on about why is it that these are deeply determined. Okay, suppose it's not, suppose that I can write X a couple of ways. So I have these choices here, and I have these choices here. Notice that, you know, I can write 0 in 2 ways. I can write it 0, 0, 0, or I can use these coordinates here, right? So it's redundant here, maybe this here as well. Anybody see a next step that I might use here? Why don't I subtract, these two are the same, aren't they? So why don't I subtract this from this, see what happens? Everybody agree that I get C1 minus D1, C2 minus D2, D2, CK minus DK. Equals what? It should be 0, right? Because I subtracted the same thing from itself. Okay, so what do I know about the vectors V1, V2 up to VK? They are linearly independent, right? So here I have an equation, a bunch of numbers multiplying my linearly independent vectors. So what does it mean about all my numbers then? They all have to be C1 minus D1 must be 0. C2 minus D2 must be 0. All the way down to CK minus DK is equal to 0. Right? What does that mean about C1 and D1? C2, D2. So that means there's only one way to write it, because the coefficients always must match. Okay. Other questions? Yes.
Quiz 6, number 3.
Quiz 6, this semester is quiz 6. All right. Okay, so it says consider the matrix. See, I told you guys that you've already done actually. Eigenvalues and eigenvectors. I never use that word here. That's actually what we were doing. And we're going to get to this later. But this is just an ordinary matrix question. Now, yes.
Quick question on the last question. So would we have to write out all that, all those variables, or could we just verbally like try to explain it, like due to the nature of linear independence? They have to be.
That's more of a religious statement, really. I mean, so what my counter to that is, what do you mean by the nature of it? Right? What is it in its nature that makes it that way?
Okay.
I don't expect, when I give you answers in a review session or whatever, I give you more detail than I really expect you to get back to me. But I'm not going to shortchange you on the detail that I'm teaching. So I will certainly give you latitude. But you probably need to say more than just, oh, because they're linearly independent, right? Because we already know that from the problem. Yes.
So is there like a definition for the equal to?
If something like that comes up on the exam, with you're kind of hosed to your home, but if something like that comes up on the exam, just ask. Because I'm not trying to trick you, what it means, that I will re-explain that or whatever. If it's not a definition in the book, if uniquely determined just means that there's only one way to write it, right? And that's the uniqueness. And it's determined by what X is. But yeah, I'm not gonna try to fool you with that kind of sneaky terminology. So if anything's unclear, just ask. So did I deal with your question?
Yes.
Okay. So we're doing number 6 here, and it just gives you this matrix B. 8 minus lambda, 10 minus 5. Okay, this matrix is just these 4 numbers. Nice 2 by 2 matrix, but I don't know what lambda is, right? It's just some of the numbering there. For what value or values is this matrix singular? Okay, what does it mean to be singular? It's not a vertical, right? We don't know in general about that. We're going to talk about what singular matrix means in general later. But we do know a nice thing about 2 by 2 matrices. What does it mean for a matrix to be singular? The determinant is 0, right? And what do we have for a 2 by 2? And this is actually, this is true more generally, but I haven't discussed this yet. For 2 by 2 matrices, B is singular. Yeah, only if the determinant of B is equal to 0. Okay, so something's got to be 0. So what is the determinant of this matrix? You know how to do it? Right. Multiply these 2 things, which is a mess. And then subtract off this product here. All right. Which is negative. There's the determinant. And for it to be singular, what do we need that determinant to be? 0. So this is an old-fashioned high school algebra equation. So that's basically what's going on here. So let's try to figure it out. I'm going to multiply this out. So I'm going to get lambda squared. I want to get a minus 8 lambda plus 7 lambda. It's minus lambda minus 56 plus 50. Everybody comfortable with that? Everybody follow my prestidigitation? Okay, so I get how do we solve this? Could use the quadratic equation for sure, but this one's E by C with some factor things. Yeah, this one is like, what is it? Lambda minus 3, lambda plus 2 is equal to 0. So my answer is for what value is lambda? Is this singular? Yes.
Did we ever talk about this class? Using the 1 over u determinant times the matrix to find the inverse? Or is that only, is there any special cases for that?
We're going to get to the relationship between the determinant and what's called classical adjoint and how to do inverses that a little bit later. Right now, the only thing that you really know a determinant for is a 2 by 2. But in fact, actually, the first section after you take this exam, I'm gonna talk about bigger determinants.
So if we have that first question on the test. Is that allowed?
So what are you asking is legal if you use a determinant for a 3x3? I might actually call the mental health facilities if you would do that, because that's like a mess. You don't want to do that, even after I teach it to you, right? But you're welcome to do it.
It's like the IJP.
If you know how to do it, you're welcome to do it, just do it right, right? But you're not, I don't think. Yeah, so actually, the easiest way to get an inverse and doing that kind of thing is really what I've already shown you about where you put the identity and row reduce. Right? Okay, everybody would be so far on where we're at on this. So landing, and by the way, I'm gonna leave B up here, but we're gonna see why they're singular pretty quickly. But the next part of the question says, for each value of lambda you found in part A, so 3 and minus 2, solve the homogeneous for lambda equals 3 minus 2, solve the homogeneous. Let's see what happens here. Let's solve this part for lambda is 3. Let's see what we have now. When I shove B into this, or I'm 3 in, that's going to give me a 5 minus 5. And 10 minus 10. Actually, one of the things that's interesting about this is for both the answers here for this next part we're working on now, we should get non-trivial solutions to these. By the way, I know that this one, notice that this matrix is certainly singular, right? Because what can you say about those two columns? They're essentially the same, aren't they? One of them's like negative of the other one, right? So how many pivot columns is this going to have? It'll only have one, right? So it's certainly going to be single. We're solving the homogeneous equation. So let's do it. What do we do to do this? Well, treat this like the augmented matrix with no zeros over here. So this reduces to 1 minus 1, 1 minus 1, right? Divide by top by 5, bottom by 10. And this is 1 minus 1, 0, 0. Sweet. Right. So you get one equation. And that's x1 minus 6. Everybody see where I got it. So notice x1 is free. And x2 is I'm sorry. My bad. It's basic. And x2 is free. And so here's the solution to the homogeneous equation. It is x1, x2, always. But now I can replace x1 with x2. So actually it's any multiple of vector 1. So that is the null space that makes. How about minus 2? Well, now B becomes 8 minus 2 is 10, then negative 5. And then I get 10 and 7 minus 2 is minus 1. So this becomes kill this. Actually, I go one minus a half. Filling that. Everybody okay with that? So for this one. Okay, yes. For this one. Notice that again, x1 is basic and x2 is free. And so I get x1 minus 1/2 x2 is equal to 0. Or x1 1/2 x2. So my solution back for x1, x2, I can now write x1 in terms of x2. X2 being 31.5. X1 is 1/2. So this is x2, 1/2, 1. If you don't like fractions, this thing is, what's the difference between these two? I just basically hold a 2 in there, multiply that by 2, and then cut this in half, if you like. Right? And since this can be any constant. Well, the determinant, what we're going to find out is first of all, the determinant is something that is used for any square matrix, right? I mean, it's only going to be defined in square matrix. But basically, the determinant is a useful tool in linear algebra. If you're thinking about a matrix as a linear transformation, that linear transformation is invertible, 1-to-1 and onto. It has an inverse if and only if the determinant is not 0. Right, so it's a very important tool for that right there. It also comes up in a lot of things. It comes up in linear algebra. Determinants come up as if you've been in Calc 3. How many of you are or were in Calc 3? So you remember when you tested functions of 2 variables, whether they're a local max, local min? It's basically a determinant. That's that. It even comes up in number theory. Determinant of matrices comes up all over the place. There are technical reasons why it's important algebraic construct. Right? But anyway, for your purposes, the bigger thing about determinants is it's going to tell you whether a matrix is invertible. If it's 0, it's not. If it's not 0, it is. Okay. Other questions? Yes. Two from Center. Oh, before you leave, make sure if you've got any questions, if you want to leave, that's cool, but don't leave before you've asked your question, so just hover at me. So, yes.
I have to be going, but I can tell you about accommodated testing.
Oh, yeah, just do that. So I'm sorry, I cut you off. What was this? Oh, right. Okay. This one this one looks intimidating because it does, but it's really not so bad. So you have this matrix here. And what does it look like? A, B, C, B, and the question is, what conditions on A, B, C, D, E, F guarantee of a matrix A? It's non-simple. Did I get that right? Okay, so another way to write this, or another way to think about this question is what conditions on these letters make sure that the matrix is invertible, right? What does it take? Now, of course, it's a square matrix, so at least we've got that part. If it wasn't a square matrix, totally no way. What conditions do we need on a square matrix for it to be invertible? What's the most streamlined conditions? Yeah,
it needs to be- I like that.
you're close. You can reduce it back, right? You can row reduce it to the identity. But there's actually one way when you think about it, it'll be even quicker. Yeah, that's right. But that's probably not gonna be quicker because I'll have to test a bunch of stuff. Can you give me something streamlined? So he says it's you can row reduce it to the identity. True. What's in it? Linearly independent columns. That's all you need. So how about, let's get really down to about brass tacks. How can you tell if the columns are all linear, if they're all what? They're all pivot columns. What does it take for all three of those columns? So let's look at columns. What does it take for this column to be pivot? How about this one? Listen, I mean, if A is 0, game over, right? Because you don't have enough pivot points. So let's suppose A is not 0. Might as well be 1 if it's not 0. Now that's got to be a pivot column too. What do you need for this to be a pivot column? D is not 0. And finally, you need this to be a pivot column. So if A and D are both non-zero, what does it mean for this one to be a pivot column? Non-zero. Yeah, non-zero. And that's it. No conditions. B, C, and E can be any dang thing you want. They make no difference at all to whether this matrix is singular or not singular. But you need A, D, and F to be not singular. Yes.
Does that mean the determinant of that?
I knew that was going to come out of your mouth, and you're exactly right. That means the determinant is not 0. We are going to see later, for those of you that have a raging interest in determinants, which is a good thing, that if you have an upper triangle or a lower triangular matrix, then the determinant is well, you have to be careful with lower triangle, don't you? Because,
Well, wouldn't it be,
an upper triangle it's always up to a sign. Upper triangular matrices, it's product of the diagonal elements.
would it be A times D times F? Wouldn't that be?
The determinant of that, yes, it would. Yeah, yes.
On a test, or even this quiz, it says it was initially on all of the variables, but for instance, you just did 3 variables, so I feel like that kind of throws you off a little bit. How do we know when just to do 3 variables, like all like 6 of them? Or do we just have to know that?
You gotta look at it, no, I think, right? I mean, so I made this matrix as general as I could, without, I made this matrix as general as I could without, and still make it up a triangle, right? So I'll let this be anything. The only thing that you need, and that's actually kind of a problem solving skill that you want in engineering and things like that, is when you're faced with a problem, right? Because I'm making my matrix upper triangular, so I'm putting in zeros down here, and numbers that may or may not be 0 up here, right? And my question is when is this non-singular? You need to know, or you need to figure out what the important things are these, and these are not important. Not important. This particular problem. Okay. Good questions. Yes.
Do you know the question along the same place? This 16.
Suppose, so I'll read through it and then we'll write down some details. Suppose A is an n by n invertible. Oh yeah, this is kind of a tough one. So I want you guys to think about this. Suppose A is an n by n invertible matrix. In class, we know that if we let B be the matrix obtained by adding 2 times the first row to the second row, then A is also invertible. What is the relationship between A inverse and B inverse in terms of similar operations? This one requires a little bit of thought, I think. A is like this. And B is the matrix change by, what did I say, adding twice the first row, second row, is that right? So B, it looks something like this. So this is like a row and column thing, right? What do? I add, so I add twice this to this. So this should be A11 plus 2, A21, A12 plus 2, A22, A13 plus 2, A23, all the way out to A1N plus 2, A2N.
That's, I think, 2 times the first and second.
Oh, did I read the problem wrong? Dang it. So I have to write this crap again. B be the matrix adding 2 times the first to the second. So actually leave the first row alone and do that. So the second row, so 2 times the first plus the second. So it's A21 plus 2A11, A22 plus 2A12, A23 plus 2A13, A2N plus 2A1N. And then first row is left alone, A11, A12, A13. And everything else is the same as it was in A. So this is just plain old A31, A32, A33, A3N, all the way down to AN1, AN2, AN3, AN. Now, one of the things that I illustrated in the class, when we were talking about this is, yeah, we do these row operations. I just said, oh, what if these are rules? We can, add a multiple, this row, that row. But you can also get this by multiplying a matrix. Can anybody tell me what matrix I would have to multiply on the left side of this to make it do that? Let's figure it out.
The identity.
Oh, you're so close. Of course, that's not quite going to do it, is because it'll make all the rows right except for this one, right? Because this one's that crazy row that's got the plus perfect. Can you, but I like that you threw the identity. Can you get out your screwdriver and fix that?
First one.
Excellent. This seems to be what I want, right? Because what is it? When I take this row and go through, it's 2 times this plus this, 2 times this plus this, 2 times this plus this, blah, blah, blah. Right? Okay with that? Now, as I pointed out, if I read this,
I was gonna say, I understand why it's there, but is there like a way?
yeah, so you gotta kind of practice that. If you look back at your notes from that day in class, we did several of them where, like, for example, what would happen what would happen if? What would happen? That's right, this time it would be at 3 times. Remember when I was writing it wrong and I put 2 times the second plus the first? What I was doing first was that, right? So you just gotta. I mean, film it, Polly, I have to think about it a little bit. Right? It's like, which way is it? But do you see it now that it works out? Yeah. And so we had the others, you know, like if you swap rows here, it effectively does some swapping here and actually multiplying a row by a constant is easy. If I had the identity matrix and I turn that to a 5, that would just multiply the first row by 5. Right? Yes.
Did the question say the identity matrix, or are we always gonna use the identity matrix for something like this?
Well, this is actually, so it turns out that when you do row operations, maybe this is the first row operation you do, so you do that. And now maybe you're not satisfied, so you need to do something else. So you put another matrix here to do it again and again and again. But these matrices always are invertible, right? Because notice that this does have exactly independence. Yes.
So elementary matrix just. Matrix.
The elementary matrix is, so the elementary matrices that we used were ones that are the identity matrix with exactly 1 0 replaced by another number. That's one kind, like this one. Or the identity matrix with exactly one of the ones replaced by a non-zero one. Or the identity matrix with some of the rows switched. In fact, just 2 of them, I think, the elementary ones. Right. So it's switching rows, changing one of the ones into a different number other than 0, or removing or turning one of the zeros into this, into a different number. What is in general, it's hard to find inverse, right? It's a tedious process. But this one's not so bad. You might tell me what the inverse of this one is? Yeah.
Can you just flip it over? Like reflect over the.
It's close. What's that?
You just moved it 2 up, right?
Yeah, you can do that, right? But it's not quite. Think about this. How would you undo this? Now that you've done this, what would you do out there?
Or
You
subtract.
multiply the first row by -2, right? So actually, the inverse is. It undoes the other one, right? Multiply this, and I get 1s across the top. This one right here, at the critical juncture, I get -2 + 2 is 0, and everywhere, and I get a 1 there, and everything else is 0. And then after that, everything's hunky-dory. Right? Everybody okay? So the inverse is actually just changing that row number. It's negative. Right. So the question says, B is also invertible, we know that. What is the relationship between A inverse and B inverse in terms of these similar operations? Well, notice that B, that we have up here, B is the matrix that I erased that had 2 times the first plus in the second row, right? Now we'll know a relationship between B inverse and A inverse. And we're assuming, actually, we know that E is invertible, we're assuming that A and B are invertible. Well, here's what I'm gonna do, because I'm a simple-minded fellow. I want to get inverses out of things, so I'm just going to do the inverse of both sides. What is the inverse of DA? So the relationship between A inverse and B inverse is now you take A inverse, whatever it is, I'm not sure what it is, and multiply it on the right. So now you're going to multiply this. Here, I'm going to put a little house on this. And the reason is this isn't the original A, this is A inverse. So some of these values might be different. Now you're going to multiply A inverse on the right to B inverse. Now, can you tell me what's going to happen here? What happens here? What's the relationship? When I take this matrix, so we can forget about this one. We take this new matrix, A inverse, and multiply it by this, side is G there. It's the output from the relative. So effectively, when I took the original matrix and multiplied by this, I've got a new second row, right? And that second row was twice the top row plus the original second row. What's going to happen here? What's this thing on the other side going to do this? Multiply it out, see if we can do it. Multiply this, I get A11 minus 2A12. And then next one I get A2, A1, this one, this column, you get A12. Put that on it. And then A13. Agree? Okay, the next row, I'm going to get A21 minus 2A22. And then next I'm going to get A22, A23, A2N. And I'm going to get next one, I'm going to get A31 minus A31 minus 2A. A32. So what's going on here? What's the relationship here? What does this matrix do on the other side? Then you take -2 times the second column and add it to the first column. So doing this elementary matrix on the other side, doing it on the right, basically operates in columns instead of operating on the rows. Y'all see that? So this is the relationship between A inverse and B inverse. It should be instead of the row operation, it should be -2 to the column operation. Any questions? So for the answer to that one, I would say, so the specific question is, what is the relationship between A inverse and B inverse in terms of the similar operations? So what you have is you have B inverse equal A inverse E inverse, right? We already did that part. Right? And so I would say, here's your A inverse. I would say B inverse is obtained from A inverse by adding the second, -2 times the second column of A inverse, the first column. A, like that. Questions? Yes.
This is from.
Okay.
It's one of the short. This is what the mean when coordinating speeds and everything.
Okay, so. All 20.
Yeah, the thin one, sorry.
What does it mean for, I probably haven't, I probably defined it earlier. In that previous list that I had. I'll tell you what it means to be symmetric. It means it equals its transpose. So when you transfer, so it's symmetric. So for an example, it's symmetric matrix. So, when you transpose, you turn, everybody remembers how to transpose, right? When, it needs to be symmetric is when you transpose the matrix, it equals itself. Yes.
Especially because students asking, what does it mean for a function to be a linear transformation? How can we articulate that precisely so that we get all the points, but not have to like write it numbers?
I would literally write something like this. That will give you full coverage. Preserve sums. Preserve scalar multiplication. Yes.
You question forward from the 2022.
Suppose from T to Rn to Rm is a linear transformation. If T is 1 to 1, then what is the relationship between N and, one, T is 1 to 1. What is the not necessarily, there's something more general than that, yeah.
This one was like N is less than M. Or,
Or equal, right, so. Anybody want to explain? Right, okay, I like that. Means X to X. So this would be 1-to-1, columns vague. Must be. I remember. That's right. There's many ways you can say this. Columns all have to be linearly independent. For it to be 1-to-1. Equivalently, the columns all have to be pivot columns. So. So the number of columns cannot exceed the number of rows. Right? And the next part is if T is onto, what is the relationship? Maybe it's that.
What happens now?
Tx equals Ax, then A must have a pivot in all rows. So in this case, we know more than the number of columns. That's a very good matrix way. Generally, here's kind of, this is not a correct formal answer. And like I said, I don't need formal answer because you need to be able to do better than this. Onto means everything is covered, right? So when you go onto a domain, you're covering something smaller. I tend to think when this is onto, when it's onto, this guy's got bigger than this. Right? When it's 1-to-1, this guy has to be smaller than this, right? That's an intuitive way about it.
I'm so confused about the relationship between 1-to-1 and onto. Is there some way you could reword it or say it like geometrically? Sure.
Nobody's wrong. You target non.
And in this scenario, both of the circles are vectors.
You know, these are all vectors within some vector space, right? Both circles are like some subspace of R. This is in general, in pre-calculus, you talk about functions, you talk about one-to-one and onto. And what it means to be onto, is nobody's lonely over here, right? What it means to be one-to-one is nobody's jealous, right? So one-to-one means this. Notice it's not on, right? Because these two are lonely. But nobody's jealous, right? So let me do something that's not.
The ones on the left represent N, right?
What's that?
So the ones on the left represent R N.
It doesn't matter. It can represent any, this is true for any function, right? Any assignment like this.
And so because when it's one-to-one, there are some vectors that are left empty. That means it cannot be linearly independent.
No, so. This one is both one and on. Because no two different ones go the same. Everybody over here goes to somebody different, right? And everybody here's covered, so it's one. Let me give you some actual. Examples of linear transformations. If you look at this. This is, you know, input is a three-dimensional vector, output is a two-dimensional. And I make my two-dimensional vector by this first and last. This is onto, right? And the reason it's onto is there's something that goes to that AB. Can anybody tell me something? How do I build something that goes to AB? Using this rule. So I've got to make a three-dimensional vector. How do I build something to get to AB? Yeah,
A, B, C, then.
we're close. Right? Everybody agree with that? The choice is zero, does that matter? You could have picked any. This is on to this, every possible thing is got it. It's not one point. Right? Because notice that A, zero, B goes to AB. And so there's A one, B. There's jealousy, these two things. They have the same value. That's an example of one that's onto but not one-to-one. Here's another example. Goes to x plus y By the way, it might be clear why this can't be on. Why it can't be on.
Not all the spaces are covered,
What's that?
not all the spaces are covered.
Right, I mean, that's certainly gonna be the truth. Can you name something then that's not covered by this? I can there's something hard to. 1, 0, 2, 2. No way. No way. It's. We're a vector in our two places. It's like 21.
Choose two dimension.
Well, right, but there's all kinds of, like, for example, 1, 1 goes to 1, 2, 2, 3. That's a 4-dimensional vector. Why is there no 1, 0, 2, 2? Let me ask you this, in the output of this function, what can you say about the first coordinate and the second coordinate? The second coordinate is always double the first coordinate. Everybody agree with that? Is that true for this thing? No way is it in the image of that map, right? This is actually 1 to 1. So from 1 to 1, you have to show that y equals 0, 0, 0, 0 has only trivial solution. Well, let's see what this is. If t of xy is 0, 0, 0, 0, that means that what is t of xy? It is x, 2x, x plus y, and 3y. And this has to be 0, 0, 0, 0. And this one right here immediately means x is 0. And this one here means y is 0. So this is 1 to 1. That's actually a trick for 1 to 1. It's a theorem I gave you in class, but check something's 1 to 1. All you have to do is if the linear transformation, if the only solution to the linear transformation going to 0 is the 0 vector cell. What's the matrix for this? Right, didn't I say all linear transformations are matrix? I wrote this down here. You should be able to come to the matrix for linear transformation. By the way, what's the size of this matrix? If we have T x is AX. What should the size of the matrix be? Good. Right, just got to take a 2-vector tangent. This was fairly easy to write down. Anybody know what the matrix A should be? It should be. Column should just be that. That's kind of the easiest way. What happens? What's E1? What's the output of the E1? E1 happens when X is 1 and Y is 0, right? So what do we get? Now what's TE2? What happens when X is 0 and Y is 0, 0? Where's the matrix step? You just test it. Put X, Y in there. What do you get? X, 2x, X plus Y, and 3. again, almost all this stuff is tested, right, which is kind of good. Okay, other questions? Yes,
I just got one quick thing. It's, so when it says like cosine, negative sine. Whatever that.
Mhm.
I know it's talking about when it's rotating.
Mhm.
Is that because like, say if I had the point like 1, 0, if I started rotating it, it'd be like the y coordinates now the sine of that. And it goes
yeah,
down.
it's sort of like that. I mean, it's actually, you can do it with trigonometry.
Yeah.
I think to see how it rotates. And the one you're talking about, the one that's cosine theta, negative sine theta, sine theta, cosine theta. That rotates everything in the XY plane, whatever theta is, whatever the angle is, it rotates that many radians, degrees, whatever it is, counterclockwise.
So if it rotates it, 30 degrees, when that means just goes to the sun.
Yeah, so for example. Degrees. Cosine theta. Theta equals pi. Radians, this would be matrix. Which is basically changes the sign of everything. And basically, this flips every vector around. Yes, did you have a question? Any guys? Yes.
What's the largest inverse matrix you've given on the test, or like largest size matrix? to
No,
give
that's
it?
not much challenge.
Please don't.
What's the largest one I've ever given? I don't know.
Like a 5 by 5, is that like probably what we would expect?
I might give you one that big, but only if I set it up so where it'll collapse pretty good.
Okay,
See, you, but
we're gonna have one with like fractions in it. Hopefully, I guess depending on how you do this.
see, I can't make any promises, because, and I also can't promise I'll make mistakes. If I make a mistake, I'll catch that, and that's sympathetic. One thing that I'm thinking very critically of this is like a great script. Right, so, you know, I want to make sure that you guys understand it, right? I generally, I don't want you really using calculators, and you shouldn't really have to, and so I tend to make the computations something that you can do. Right, that's not to say I won't make a mistake, but you know, it's pretty unlikely that I won't catch it. So. Okay, yes,
If you go over, quiz 3, question 2,
which one?
quiz 3, question 2.
Quiz 3, question 20?
Yeah.
Okay.
Thank you.
You're welcome. Okay, it says, that's for this semester, right?
Yeah.
So, okay. Oh, I got it. Then I think that's articles. Find the value of x, it's x1. Oh, okay. So it's these 3 vectors here. X1. Minus 1, 2. Yeah. Plus 1, 2, 1, 0, 1, and x squared x1. X squared x1. And the question is to find all values of x such that this is a linearly dependent set. So. Here's what I would do now. I would, put this in a matrix and what does it mean to be linearly dependent? It's gotta have less than, 3 pivot columns, right? So let's reduce this. I'm liking this one. I use this one to take a step out here. So I'll multiply by 2 and add 1. Multiply by 2 and add. Multiply by 2 and add to the bottom. It's also a 1. And multiply by 2, so that's 2 equals 1. Let me do a little cosmetic rearrangement here. I'm gonna change the sign of this and move it to the top. Right? Now I'm gonna move this in the middle. Well, actually, I'll move this in the middle. Now, in my final thing, I'm gonna take the middle row, multiply by -1, and add it to the bottom. One, 0, minus x, 0, 1, 2x plus 1. And now I take -1 times the middle row and add to the bottom. It's gonna be 0. And then I'm going to x squared plus 2x minus 2x plus 1. So I get. Right, okay with you? Right, okay. Now, for sure, I've got 2 pivot columns, right? I got this, I got this. It's linearly dependent. For this to be linearly dependent, what has to happen? This one has to be 0. Has to be 0. Because if it's not 0, that's a third pivot column. Everybody okay with that? And so my answer. X is equal plus 1. Any questions?
Would say that it's literally dependent, you take that bottom and you just set it equal to each other.
What's that number?
So for it to be linearly dependent, you said that you have to take that last value at x squared minus 1, make that 0, so that means that just 70 0, right?
Yeah, that's right. Because if that entry there is, if it's 0, then I've only got 2 pivot columns. If it's not 0, that's a third pivot column, and the vectors are all linearly independent. Right, okay? Yes.
Question. More of a simpler one, but given like 3 different vectors, I feel like refresh, how do we show that this set of vectors spans like 3?
Okay, so like the general technique is so you got 3 vectors in R3, and you want to know they span, right? Here's what you do. Well, we do major row reduce. If you've got a pivot in every row, when you reduce it, then it spans R3. That's it. Yes.
You do exam one, question one, parts.
Which exam?
L, the
2022. K and L?
Yep.
What is the basis, the subspace? Like in vector spans spaces linear independent. And L? What is it? Transposes the second matrix of the ounce forward.
On that same exam, you get two D, just as a reader. General solution.
Which one is it to, which one?
The same exam that this was on, question 2, part D.
Nah, let's just do the whole thing, right? Okay, that way we'll, you know, because otherwise we're worried with my concepts. Do you have it in front of you? No. You have it in front of you?
Yes.
Can you read? There's a lot of rows. What's the top row?
-2, 2, 1, -1, 2, 7.
And what's the next row?
-1, 1, 1, 1, 3, 6.
Okay,
And it's 4, -4, -1, 5, 0, -9.
and is that it? Okay, so we've got this awful 3x6 matrix. So A, B, C, it's like find a basis for null A, find a basis for column A. And so the good thing about that is these problems kind of go in hand, right? So let's row reduce this thing. And what I'm gonna do is change the sign to a point. And now I'm gonna multiply, so I'm gonna put the second row, I'm gonna multiply this by -2 and add this. Second row, by -2 and add this. -2, -2, 2, -2. And multiply this by 4. So, 3, 9, 12, and Now, actually, if you will forgive me, I'm gonna divide all this up for you. So this is gonna be 1, 3, 4, 5. Oh, wow. I'm going to change the sign of this. Zero, 0, 1, 3, 4, 5. And I'm gonna use this to take out this right here, so that I have a pivot column. So that's going to be 1 minus 1. 0, 2, 1 minus. That looks like no reduced section. Okay, now that I've row reduced it, I think that I'll probably just go back and refer to that a couple times here. All right, what does it say? Find the basis for null. By the way, before we get carried away, what's the dimension of null? Can you eyeball that and tell me? It's 4 dimensional. Everybody agree? It should be 4 dimensional because there's 4 not pivot or not pivot column. So let's see what we got here. We've got x1 and x3 are basic. x2, x4, x5, x6 are free. So, what do we get here? I did a couple of equations. I get x1 minus x2 plus 2x4 x5 minus x6 0, and the other equation I get is x3 plus 3x4 plus 4x5 plus 5x6 is also easy. So notice always in these things, the free variables, there's nothing you can do about it. They're free parameters, right? And there's 4 of them, and they're basically the constants that you're going to multiply and find the vectors by. Your basic ones can be written in terms of the other ones. So I've got here that x1 is equal to x2 minus 2x4 minus x5 plus x6. And x3 is minus 3x4 minus 4x5 minus 5x6. So my solution to my little null space problem here is this. I like to kind of write it down this way. So I've got my bearings. x2, x4, x5, x6. Those babies are all free, so I got to put them in as is. But x1 and x3, the basic ones, I can replace them with the others. So x1 is x2 minus 2x4 minus x5 plus x6. And x3 is minus 3x4 minus 4x5 minus 5x6. Everybody good? And I like to present it in this form because it makes things kind of clear. x2 becomes the vector 1, one. Plus x4. -2, 0, 3, 1, 0, 0. X5. -1, 0. -4, 0, 1, 0. Right? Finally, x6 times 1, 0, -5, 0, 0. Yes, sir.
Oh, you just forgot to write -3 for X.
Did I? I sure did. Thank you. You guys get me on these things. All right, everybody okay so far? So, the basis for null A. Let's see, what do we win? -5. By the way, the null space is always good because of the fact it uses these equations. It's pretty clear, isn't it, that these are linearly independent? Because if you multiply this all by different numbers, C1, C2, C3, C4. C4 has to be 0 because it's the only non-zero entry down, right? So now this one's gone. And now C3 hits this one, and there's no other things to cancel out. So C3 has to be 0. Now C2 has to be 0 because this thing's lower than this, and now you got to C1 times C0, so it's gonna be 0. So this is linear, and the set expands the null space. What should the dimension of the column space be? Notice, by the way, that the null space is inside of R6, right? It's a 4-dimensional because these are all vector 6 components now, right? So this is a 4-dimensional subspace of R6. What about the column space? What do we do about the column space? So with the information on board, we should be able to figure this out. So the column space. The column space always tell you gotta be a little bit careful with, right? The column space corresponds to the pivot columns. Which are the pivot columns in our final form? Column 1 and 3, right? But these are not the bases, right? In fact, these vectors may not even be in the original column space. What you have to do is pick out the original ones they came. So it's the first and third columns, the original. So there's your column space. And even though it's it's not as obvious as from null space, these vectors are also immediately independent because after the row reduction, these, all the row operations preserve one independence. Okay, any questions? The next question is, what are the dimensions of null A and column A? Well, looks like null A is 4. Column A is 2. And tell me why we feel all warm and fuzzy about that. Yeah, it checks out, because rank-nullity says the dimension of the null space plus the rank, which is the dimension of the column space, should add up to the number of columns, 4 into a 6. So that's a good sign, right? Are you okay with that? Okay, and at long last, I think we've gotten to what you were curious about. Suppose one solution to AX. Suppose one solution is find the general solution. This is a little bit of an amazing question, but it hinges on the theorem of unbig class, right? Often such equations like this are limited solution, right? Now, I didn't even tell you what B was. I just said, okay, this is a solution. Now, there might be anything, can you tell me what every solution looks like now? Actually, this is, do you remember this theorem that says that if you have AX equals B, all you gotta do is find one solution, and VP I'll put up there to be suggested because it's sometimes called particular solution, just find one solution. And every solution is whatever you found plus a homogeneous. Right? So any solution is particular solutions found or was given plus the homogeneous solution. So in our case, 1, 2, 3, 4, 5, 6 plus that thing over here. Say A times 1, 1, 0, 0, 0, 0 plus B times minus 2, 0, minus 3, 0, 0 plus C times next one minus 1, 4, 4, plus D times the last one, which is 1, 0, minus 5, 0, 0. So if I know that one solution looks like this, then any solution looks like this. And basically, notice that it doesn't have to be, you might have found another particular solution. Another particular solution is 2, 3, 3, 4, 5, 6, just by adding one of these to this. Alright, so, and it would still have the same thing. Well, by the way, you didn't ask this question, what is B? How would you find out? All you'd have to do is just plug in the thing as you just multiply A times whatever this VP was, 6. Multiply it out, and you'll get, I guess, it'll have to be a 3 by 1 vector. And that'll be B. Okay. Is that clear? No one can. All right, what else? Any other questions? We good to go? All right. Don't stay up too late studying. I'm back for the exam. Make sure you get rest.
The amount of